Hello and welcome to online lecture number 6 for Chemistry 1101 during the spring semester of 2020. We'll begin a new chapter in this lesson, chapter 9, and in this chapter, we're going to focus on something called solutions. A solution is another term for something we already are familiar with, and that are homogeneous mixtures. Homogeneous mixture was a mixture, if you recall from our discussion very early on in the semester about the classification of matter as being either a pure substance or a mixture of some type. A mixture is a physical combination of two or more components. And a homogeneous mixture, therefore a solution, the term for solution, is one in which the composition of that mixture is uniform throughout. When we talk about solutions specifically, though, and we want to try to understand the properties of these solutions, we need to understand what those components actually are. In the terminology of dealing with solutions, we call the minor component or minor components of a solution are called the solutes, and the major component is called the solvent. And probably our most common exposure to solutions, the solvent is usually water. When we think of solutions, we normally think of homogeneous mixtures of liquids and liquids, such as gasoline or alcoholic beverages, are combinations where both the solvent and the solute or solutes are liquids. Or we may think of solids and liquids, such as salt water or sweet tea, where we've dissolved a solid substance, solid solute, into a liquid solvent. But we're certainly not limited to those physical states. So if we want to make a solution, regardless of what physical state the solute is or what physical state the solvent might be, then we want to make sure that it's going to be roughly easy to make this solution. So as a result, we want to choose a solute that is expected to be soluble in that solvent. A soluble solute is a solute that's able to dissolve relatively easily in that solvent. More precisely, it's able to dissolve to a large extent in that solvent. We can describe to what extent it dissolves in that solvent by its solubility, where solubility measures, it's a quantitative observation, quantitative property, that measures how much of that substance can dissolve in a given volume of the solvent, usually also at a given temperature. So for example, if we compare the solubility of several different types of solutes in water, these are all going to be grams per 100 milliliters of water, and 100 milliliters of water is less than a half a cup of water. Sodium chloride has a solubility of about 36 grams. So we can dissolve 36 grams of sodium chloride in less than half a cup of water at room temperature. Potassium nitrate, another ionic compound, also has a relatively high solubility, about 33 grams per 100 milliliters. But then another ionic compound called calcium carbonate, its solubility is only 0.0015 grams per 100 milliliters of water. So to various extents, all three of these substances will dissolve in water, but we can see though that sodium chloride potassium nitrate will dissolve to a much larger extent, much greater extent than that compared to calcium carbonate. Same comparisons for molecular compounds. Table sugar has a very high solubility. Over 200 grams of table sugar will dissolve in less than half a cup of water. Whereas another molecular compound known as methane, natural gas, it only dissolves to a very limited extent, 0.002 grams per 100 milliliters of water. So a soluble substance, such as sodium chloride, potassium nitrate, and sugar, they are soluble, called soluble, because we have roughly large amounts of those substances will dissolve in a really small volume of water, whereas calcium carbonate and CH4 will be considered insoluble solutes, because these are substances that don't dissolve easily, or more precisely, once again, they only dissolve to a very small, practically negligible amount in a given solvent at a given temperature. So we have both soluble substances and insoluble substances. Based upon these classifications are based upon either relatively high solubilities or relatively low solubilities for soluble and insoluble, respectively. If we want to decide, be able to predict whether or not a given substance, given solute, will be soluble or insoluble, it's going to depend upon the nature of the solvent in the solute. So we first consider molecular compound solubility. In other words, be able to decide why it was that Sugar was soluble in water, whereas CH4 was not. And the rule of thumb we'll use is like dissolves like. That's an expression we've known probably for a very long time. But what we mean by like dissolves like, what's like about the solvent versus like about the solute, are similarities in intermolecular forces. So in other words, what this indicates is that this rule of thumb, there are some exceptions, but the rule of thumb is that if the solvent and solute have very similar, if not identical, intermolecular forces, then the solute would tend to be soluble in that solvent, like dissolves like. But if the solvent and solute have different intermolecular forces, then the solute is likely to be insoluble in that solvent. And we'll see a couple examples of those. So the first question is, which substance of these three is expected to be the most soluble in water? To answer that question, we need to decide what are the IMFs of water and what are the IMFs of our three solutes. And because like dissolves like, whichever solute's IMFs is the best match with the IMFs of water, that's the solute we expect to be the most soluble. Conversely, whichever solute's IMFs is the worst match with the IMFs of water, that substance we'd expect to be the least soluble in water. Once again, because like dissolves like. So to decide about IMFs, we need to look at the structures, and then from the structures, decide on IMFs. So to answer that question, as to which of these three solutes we expect to be the most soluble in this solvent, we want to look at the IMFs and decide on the IMFs of the solvent and then compare that list to the IMF list for each of these three solutes. Because like dissolves like, whichever one gives us the best match, that one would be the most soluble. So for water, if we begin with the solvent, and we've seen water before, so we know maybe from previous discussions that water is a polar molecule that can hydrogen bond. So it's going to have all three. Dispersion forces, because all molecules do, dipole-dipole, because it's polar, and then because it has oxygen-hydrogen bond, it's going to have hydrogen bonding. And then we go in turn look at our IMFs for our three solutes. So CH3Cl, carbon central atom, the bonds are not identical, so then and only then we have to look at the polarity of the bonds. What we would find is that this carbon-chlorine bond is in fact polar. So because this carbon-chlorine bond is polar and the bonds are not identical, the molecule is polar. And because the molecule is polar, it's not only going to have line dispersion forces, but it's also going to have dipole-dipole forces. So it's a polar molecule, but it cannot hydrogen bond because it does not have a hydrogen-oxygen bond, a hydrogen-nitrogen bond, or a hydrogen-fluorine bond. With the second candidate, CCl4, carbon central atom, all four bonds are identical. So even though these bonds are polar, because they're identical, that's going to make the molecule nonpolar. And because the molecule is nonpolar, this molecule just has line dispersion forces. And then finally, our CH3OH molecule, because of the oxygen-hydrogen, we're going to have a polar molecule that can also hydrogen bond. So it's going to have all three: line dispersion forces, dipole-dipole, and hydrogen bonding. So we can see then, comparing our list, like dissolves like, of the three solutes and their IMFs, CH3OH is the best match because its list of IMFs is the exact match with the solvent's IMFs. So notice that a solvent that is a polar molecule that can hydrogen bond will most easily dissolve a solute that is also a polar molecule that can hydrogen bond. And the least soluble substance will probably be CCl4 because it's a nonpolar substance, and its IMF list is the worst match with the IMF list of the solvent. So that's what we saw with water, and we'll do a very similar question. This time we're going to change up the solvent a little bit. So now we're going to look at the same three solutes, CH3Cl, CCl4, and CH3OH. This time we're going to ask ourselves, which substance do we expect to be most soluble, and not water, as you saw earlier, but rather C8H18. We're still going to apply the same idea that like dissolves like. So back to a similar question where we want to consider these three possible solutes. And the question is, which of these three solutes we expect to be the most soluble in this solvent? The solvent is C8H18. We could draw the structure, but even without drawing the structure, we recognize that C8H18 is a molecule containing just carbon and hydrogen. So because it just contains carbon hydrogen, the only bonds present in the structure would be carbon-carbon bonds, which are always nonpolar, and carbon-hydrogen bonds, which is also nonpolar. So for both those reasons, we have that rule of thumb that any molecule containing just carbon-hydrogen is always going to be nonpolar. And if it's nonpolar, then the only IMF present for this molecule, for the solvent, would be the Lund dispersion forces. So this is the IMF for our solvent, and then these, as we just decided earlier, are the IMFs for our 3 possible solutes. Notice here that CCl4, the nonpolar solute, has the best match of IMFs with the solvent. So as a result, we'd expect that CCl4 would be the most soluble in C8H18. A nonpolar solute is the most soluble in a nonpolar solvent. Like dissolves like. Conversely, CH3OH, because it has the worst match, we'd expect that CH3OH would be the least soluble in C8H18. So we can use this idea of like dissolves like. A polar solvent is more easily dissolve a polar solute. A nonpolar solvent is more likely to dissolve a nonpolar solute. So our idea of like dissolves like is a rule of thumb we can use to predict the relative solubility of molecular compounds. For ionic compounds, the process may be a little bit easier. For ionic compounds, it still depends upon the nature of the solvent and solute. But for ionic compounds, we have what's called solubility rules. And so these are rules or trends that we have observed when trying to dissolve various ionic compounds, and specifically in water. So all of these concern the dissolving these substances in water. And the solubility rules, we can predict whether a substance will be soluble or insoluble based solely upon the identity of the cation and or the anion. There are some exceptions to these solubility rules, but we're largely not going to worry too much about the exceptions. So we want to go through these rules, and then we'll apply these rules for a couple of examples. So the first rule says that if the ionic compound contains either a group 1 metal, such as sodium, potassium, lithium, etc., or ammonium ion as its cation, then that particular ionic compound will be soluble, and there aren't any exceptions to that rule. Rule 2 says that if the anion is either nitrate or acetate, then the compound is going to be soluble. In fact, it doesn't matter what the cation is here, the substance is soluble. It doesn't matter what the anion is. In these examples, the substance will be soluble. So those are the easiest rules. So if you recognize the ionic compound contains either a group 1 metal, ammonium, or nitrate or acetate, then right away we know it's going to be a soluble substance. The others are a little bit harder because they have exceptions. Chloride, bromide, iodide, sulfate ions are typically part of soluble compounds, but there are some exceptions. Typically, silver and lead are part of insoluble compounds. There are some exceptions. And finally, the anions carbonate, hydroxide, and sulfide are typically part of insoluble ionic compounds, but there are some exceptions. So what we want to be able to do on homework, even on exam, is predict for each of these substances whether we expect to be soluble or insoluble in water, basically apply the solubility rules. So we have potassium fluoride. Potassium, notice, is a group 1 metal. So because it's a group 1 metal with no exceptions, we can predict and accurately predict that potassium fluoride should be a soluble substance. We don't have a rule regarding fluoride, but it doesn't matter because if potassium is a cation with no exceptions, the potassium fluoride substance would be soluble. Calcium sulfide, we don't have a rule regarding calcium, but we do have a rule regarding sulfide. Sulfide compounds generally are insoluble. There are some exceptions, but we don't have any other rules that seem to at least even imply that calcium sulfide is one of those exceptions. So we have to conclude that this substance is insoluble. It's not one of the exceptions to rule number 5 here. With magnesium nitrate, we don't have any rule regarding magnesium, but we do have a rule regarding nitrate. Notice that nitrate, rule 2, if the compound contains nitrate, that means it's going to be soluble with no exceptions. Magnesium nitrate should be soluble. Silver chromate, we have a rule regarding silver. Silver compounds containing silver ions tend to be insoluble. There are some exceptions, but we don't have any other clue about whether chromate is one of those exceptions. So we have to assume that it's not. because that's going to be an insoluble substance. And then ammonium carbonate, we have two rules that apply. Ammonium is the cation. So according to rule number 1, if ammonium is a cation, it's always going to be soluble. Carbonate is the anion. And according to rule number 5, carbonate-containing compounds are typically insoluble. And a particular substance is either going to be soluble or insoluble. It can't be both at the same time. So we have to conclude, because rule number 1 says no exceptions, rule number 5 says some exceptions, we have to assume that ammonium carbonate is one of the exceptions to the carbonate rule. In other words, because ammonium is a cation, as we discussed earlier, it doesn't matter what the anion is, we predict it to be soluble. So with molecular compound solubility, we use like dissolves like. With ionic compound solubility, we just need to apply these solubility rules. And in our next lesson, we'll get into other factors that we could perhaps change to affect the solubility of a substance, either increase or decrease the solubility, the inherent solubility of a substance in a given solvent.